Welcome all my dear students. Today we are going to start with lecture 3 of CS 302 Data Structures course. I am Dr. Sangeeta Bhattacharya, and today in this module, in this lecture, we are going to see the following things. The time and space analysis of algorithms, an introduction to some of the order notations we use for analyzing the time and space complexity of algorithms, and some numerical problems on that. So when we are talking, so in the last lecture we have seen, if we want to implement, if we want to represent the algorithm efficiency from the program code, we are concerned about two things. One is the for number of instructions in case of programs without loop, and if the program is having loops, then how in case of linear loop, quadratic loop and nested loop, how we can determine the efficiency. And there, if you remember, we have represented it in the form of certain kind of functions. So we have represented it like f of n equals to n, where n was the number of iterations of the loop. Number of iterations of the loop. Now we are going to represent that complexity in terms of more standard notation, and before that, let us know what is meant by complexity. So complexity typically means that what is the amount of space and time required to execute a given program. So when I talk about a program here, it typically means the algorithm, because from the algorithm we are going to write the program code. So it is the amount of resources, and if you are talking about the computer, it is the CPU time and it is the space, memory space. So CPU time required to execute a given program, and the memory space required for storing the variables and the functions for executing the program. So these are the two resources of a computer system. Now, when we are talking about the complexity, there can be four different cases. So the first one is a worst case, the second one is the average case, the third one is a base case, and the fourth one is the amortized case. We in subsequent classes, when we will see that, we are concerned about the worst case complexity more, and the average case, base case, and amortized are not much considered. Now, what is the worst case complexity? What is meant by the worst case complexity? So the worst case complexity of for a program arises when, now we should remember that all these cases arises because of the input sequence. So certain kind of input sequences results in the different cases which we are seeing here. So first, let me talk about how we can do this. What is the worst case? So let us think about the simple sorting algorithm, and let us take an input sequence. So let my input sequence be something like 100, 90, 80, 70, and 50. So this is my input sequence, and I have been told to arrange these numbers, this sequence of numbers, to arrange the given input in ascending order. So we see that in any kind of programming we apply, any kind of sorting algorithm we apply, whenever our input is given in a descending order, and if we have to arrange the input in ascending order, so the loops have to go through the whole list of numbers. So we can consider this to be an example of worst case. So this can be considered a case of worst case complexity in case of sorting, so this can be termed as a worst case for the sorting algorithms, because here whatever be the sorting algorithms, it has to go through the whole numbers and the whole range of numbers or input sequence which is given to arrange it in the ascending order. Now, typically, when we are talking about an ascending, about the worst case determines the upper bound on the running time for any input. So, worst case, so determines it is something like the upper bound on the running time. So, if the logic behind this is that if we can arrange the time taken for arranging the given numbers will be for this kind of worst cases, like for this example, the time taken to arrange these numbers, whatever time it will be taking in terms of suppose fn, will be for the other input sequence, it will be always less than this fn. So in the worst case, whatever time will be taken for running this particular any kind of algorithm will be the maximum one, and for the other sequences or the other input sequences, it will be always less than this particular running time. So this is known as the upper bound. Now we come to the average case complexity. So what is meant by the average case running time or average? Now we should remember that this 4 cases is not only applicable for the time complexity, but it is also applicable for the space complexity. So they are not only applicable for the time complexity. If I talk about the time complexity means it is the amount of time taken by an algorithm to run. And if I talk about the space complexity, it is the amount of memory space taken by an algorithm to run. So the memory space which will be taken is typically for the variables which are used for running a given algorithm. Now, if I talk about the average case complexity, then in case of the average case complexity, it is the time taken. In case of average case, what we see, then in case of average case, it is assumed that in case of average case, it is assumed that all the input sequences are equally likely. And here it is assumed that all input sequences are equally likely, and the running time for the algorithm in case of a randomly selected input sequence. Randomly selected input sequence. So this is what is for the average case. If I talk about the best case, so best case means when your system, so now if we talk about the best case complexity, so best case is always the condition where the algorithm is running under optimal condition. So where the algorithm is running under optimal conditions. For example, optimal conditions. Now, for example, if I talk again about the sorting algorithm, then, and now one thing we should remember is that we hardly base our decision on the best case performance, because best case is an ideal situation which in most of the algorithm cases we may not achieve. So what in all this, what we are concerned about is actually the worst case. So in most of the algorithm, you will be finding that we are talking about the worst case complexity, that is the bound beyond which the complexity of that algorithm cannot go. And best case, because it is always working under an optimal situation, optimal condition, so most of the cases best case running time is not considered. Now, what can be the best case situation? Let us think about it. Suppose I am having a list of elements. So I'm having a list of elements like something like this, 50, 100, some list, sorted or unsorted doesn't matter. And I am searching for the element 10 in the given list. Now, if I'm searching for 10 in the given list, then once I start, so if we implement this in terms of array, so if this is implemented in terms of array, then what will happen? So if I start running a loop for I equals to 0 to I less than equals to 4, if I start looking for comparison, I will be finding it in the right at the first of the list. So if my comparison is something, so if I run a loop like this for I equals to 0, I less than 4, I plus plus, if x, let x be equals to 10, is equals to a of I, then print success. So if I do like this, and if I'm searching for the first element 10, then it is this loop is going to run only for, so this loop is going to run only one time. So it is going to run only for one time. While for the same case, if I'm searching for the element 90, that if x is equals to 90, this loop is going to run for 4 times. So this is the difference between the best case and the worst case. So if x is equals to 90, then that is belongs to the worst case scenario. If x is equals to 10, it belongs to the best case scenario. So when we are talking about, we should always remember that what will happen if the list, if we are searching for the element 90 in the list, or if we are searching for an element 120 which is not there in the list. So this is the worst case, where either the element is the last element of the list or the element is not there in the list. So we are concerned more about these cases. Now, if we come about the amortized running time, now the amortized running time is basically, the definition tells that it is a sequence of operations averaged over all the operations performed. So it basically gives the performance, it guarantees the average performance. So amortized analysis guarantees the average performance of each operation in the worst case. Each operation in the worst. So this is the amortized. So we see that these three are related. So if we talk about this, the three cases are concerned about the input sequence what we are giving. So it is more of like an input sequence. So input sequence, and this is related with the operations which are performed. Amortized case is amortized running time, or amortized case is more concerned about the operations which are done in the worst case. So in literature, if you see, and in the subsequent classes, we will be talking about these three cases mainly, which is worst case, average case, and best case. One more point we should remember is that average case arises only when worst case is not equal to the best case. So where worst case is not equal to the best case, in such a situation only the average case analysis arises. We will be seeing it with the help of examples when we will be studying the sorting algorithms. So if the worst case and the best case complexities are same, then there is the average case is the same. Well, in the question doesn't come there because it is the average. So for a random input, what is going to be the complexity? Well, if these two differ, worst case and the best case, then in that case only the average case analysis question arises. Now, we will go to the asymptotic notation. And what is asymptotic notation? Now, asymptotic notation is a more standard form of representing the complexity of an algorithm. Here, the performance is measured in terms of the problem site. So when I talk about the problem site, basically it means the input. So we have already seen in case of algorithm efficiency measurement that we are representing it in terms of Fn, where n was the number of iterations of the loop. When we come to the asymptotic analysis, it becomes the input. So what is the size of the input basically? And with the help of this, the growth rate of the function is determined. So it is a growth rate of the function that describes the running time. Again, because we are concerned talking about the running time, we also represent the space, also the space complexity of an algorithm is also represented with the help of the asymptotic notation. And the notations which are used for the asymptotic analysis, they are known as the asymptotic notations. And these notations are independent of any kind of hardware, software, compiler we are using. For any system, if you write an algorithm, that algorithm for any kind of system is going to give you the same complexity irrespective of the platform or compiler we are using. So why this term asymptotic? I will come to it in my next slide, what is meant by the term asymptotic. But basically, it measures the performance of an algorithm in terms of the problem set. Now, let us see this. So the asymptotic first notation is known as the big O. So this is a O and this is big O. What it is telling is that we are having, so order of G of n, order of G of n can be represented as Fn, where there exists positive constant C and N0. So these are positive constant C and N0. So their value will be always greater than 0. So C will be greater than 0 and N0 will be also greater than 0. So there are two positive constants C and N0 for which 0, this inequality, 0 less than equals to Fn less than equals to Cgn holds, and the value of n should be greater than equals to Nc. So let us see with the help of this example. So we are having, this is the Fn and this is the C of Gn. We see that there is a particular value called N0. So there is this particular value which is N0 beyond which Fn is less than equals to C of Gn. In this case, big O gives us the asymptotic tight bound. So this is known as tight bound. Big O is known as tight bound because whatever happens, Fn will never cross Cgn after N0. So after, now, what is this? This part. So this part, so this is the input side. So this is the input side. And this part is the time. And here n, what is n? And here n is equals to the input side. So n is equals to input side. So as the input side increases beyond n0, Fn will always be less than equals to Cgn, and therefore it is known as asymptotic tight bound, because tight bound means tight, asymptotic tight upper bound. Just erase this part. So this is known as asymptotic this is known as asymptotic tight upper bound. Asymptotic tight upper bound. Because beyond this, whatever happens, your complexity cannot go, that is Fn cannot go beyond Cgn. So this is big O. Big O, so we will be seeing some problems on big O now. So the typical problem which may come in exams, this is also very important for exams, because in exam you may be asked to solve certain kind of problems like this. So what it is given, let us see how to solve this kind of problems. So we have been told that this is Fn square, and we have to show that it is equals to order of n cube. So this is called as order. Big O of n cube of order of n cube. Now how can we show that it is order of n cube? So from the definition of big O, we know that 0 less than equals to Fn less than equals to Cgn. From the definition we know that. Now we can replace Fn by 4n square in this inequality and Gn by n cube. So it becomes 0 less than equals to 4n square, which is Fn less than equals to Cn square. We have replaced 4n square and n cube in this inequality. Now we have to find out the value of C. So C is that constant, positive constant. So C will be always greater than 0. So if we divide all the sides by n cube, so we get something like this. So if we divide all the sides by n cube, we get 0 less than equals to 4 by n less than equals to C. Now, if we see this nicely, we will find that the value C, we remember it is the upper bound. So we have to take the maximum value for C, so that 4 by n is always less than equals to C. So it will be a maximum value of C, and 4 by n will be less than equals to C. So whatever value whatever value will be the n, this term will always be less than equals to C. If we see that when n tends to infinity, 4 by n tends to 0. So the maximum value of C or this inequality can be achieved when the value of n is equals to 1. And in that case, so the value of n is 1. In that case, we can reach the maximum value for 4 by n. And if we replace that value of n in this inequality, we see the value of C is 4. Because we should remember that because we are talking about the upper bound, we should always check the maximum value for C. Now we have to find the value of, so for any problem you remember, we have to find the value of C and we have to find the value of n0. So we are going to find out the value of C, and then we are going to find out the value of n0. So if we want to do this, so we can replace C by 4 here in the same inequality, and then 4 by 4 will be less than equals to, so it's just a simple calculation, and we see the value of n0 is achieved to be 1. Now if we place it in this equation, so 0, 4 Fn is 4n square and Cgn means 4n cube. So if we see this, this will always hold when n is greater than equals to n0 equals to 1. So when the value of n0 is greater than equals to 1, it will always hold. So this function will be something like this. So suppose the n0 value is 1 So Fn will always be, so if we draw it something like this, then 4n square will always be below. So this is 4n square and this is n cube. Now 4n cube, so this will always be less than 4n cube. So given a problem, you have to solve this in this way. So the first step is to, what is the actual inequality given, replacing the values of Fn and Gn in the inequality. Then we have to find out the value of C, so we have to keep it as an individual element. So accordingly, we have to divide it by the appropriate term. And then we have to see what will be the maximum value of C so that this inequality always holds. And after we find out the value of C, we replace that in the inequality and find out the value of NC. At the last slide, I have given some of the problems, exercise problems. You can try it out at home. And in case of problem, you can contact. Now, let us see the next notation, which is known as the big omega. Now, big omega is what? It is just the reverse of big O. So, in case of big O, Fn was always less than or equals to Cgn, and in case of big omega, Cgn is always less than or equals to Fn for the same positive constant C and N0. So, in this case, we can talk of big omega as asymptotic tight lower bound. That means that Fn will never go beyond Cgn. Fn can never go beyond Cgn. Whatever will be the value, it will be always be above Cgn. Now, why the term asymptote? I just missed that in the previous slide. Asymptote means two curves which will go parallelly very close to each other, but they will never converge. So this convergence will not be there. So they will never meet. This part will not be there. So they can never meet, but they will be going parallelly very close to each other. If we see this kind of asymptotic notations, here Fn and Cgn will never meet after the point n0. After the point n0, Fn and Cgn will never meet. They can be very close to each other, but they will never meet. So that's why they are known as asymptotes. So big O was asymptotic tight upper bound and big omega is asymptotic tight lower bound. We can also have some problems on this. So it will be solved in the same way as we have solved the big O problems. So here, what we have to show is that 5n square plus 10n is equals to omega of n square. Now, what is the for omega? What we have to do? 0 less than equals to C of Cn less than equals to Fn. We replace Fn by 5n square plus 10n and we replace Gn with n square. So it becomes Cn square. Again, I told that we have to find out the value of C. So accordingly, we are going to divide it by appropriate time so that we get C. So if we see here, if we divide Cn square by n square, then we can get C from there. So we are dividing it by n square. All the sides are divided by n square. So if we divide Cn square by n square, we get C. If we divide 5n square by n square, we get 5. And if we divide 10n by n square, we get 10 by n. Now here we see, now in case of big O, we are talking about the maximum value. In case of omega, we are talking about the minimum value. So if we are talking about the minimum value, then we can see that 5 plus 10n, limit of 5 plus 10n when n tends to infinity will be minimum when it is 5. So 5 plus 10n, the limit of 5 plus 10n when n tends to infinity will be minimum when the value is 5. So we can write it like this, 0 less than, because we are talking about the lower bound, so we are talking about the minimum value. So 0 less than equals to c less than equals to 5. Whatever will be the value of n after this, it will be always, so after n equals to 0, whatever will be the value, only when n is equals to infinity, at that time only we are going to get the minimum value for n. So when n is equals to infinity, then we will get the minimum value for 5 plus 10 by n. For all other values of n, it will be 5 plus 10n will always be greater than 5. So it will be 5. Now we simply replace this here. So 0 less than equals to 5 less than equals to 5 plus 10 by n 0. And if we solve this, we find that 10 by n, when n tends to infinity, will be 0 when n0 is equals to 1. So 10 by n is equals, so we are concerned about the minimum value. So we are going to take the minimum value for n0. So it will be n0 equals to 1. So again, if I draw this, it will be something like this. So here is the 1. So from here, if we go like this, then from here, if we go like this, so this value is n0, 1. And in this case, this will be c of n square, rather c of n square, 5 of n square. So this is 5 of n square, and this is going to be 5 n square plus 10n. So you can see for any value of n, this is going to hold. For any value of n beyond n0 equals to 1, this is going to hold. So this is how we can solve the omega notations. One more popular asymptotic notations which is left is known as the big theta. What is big theta? It is a combination of big O and big omega. If we see this nicely, so this part is the omega part, and if we look at this part, so this is the big O part. I think you can observe. So what was omega? 0 less than equals to C of Gn less than equals to Fn. And what was big O? 0 less than equals to Fn less than equals to C2Gn. So if we look at this diagram, then this is N0. So beyond N0, Fn will be sandwiched between C1Gn and C2Gn. And from here, you can very clearly make out that this is the kind of average case. So the average case running time can be represented by using the big theta notation. Sometimes it is not always so. In some cases, you may find it is represented by big O or big omega also. But if we look at this thing, we can make out that it is more of a representation of an average case where Fn is between C1Gn and C2Gn. And if we have to solve any problem using big theta, we can apply both big omega concept of solving the problem and big O notation of solving the problem. So let us see a very simple example. So let us see this example. So we have to show this n square by 2 minus 2n is theta of n square. So this is the inequality we are having. Now we have to find C1 and C2. So C1 and C2 can be achieved when we divide all the sides by n square. So we achieve this inequality. Now solving this part is solving the big O notation and big theta notation. Sorry, big omega notation. So if we look at this part, it is similar to solving O. So if we have to find out the value of C2, it is solving big O notation problem. So what we see, we are talking about the maximum value of C2. So we are talking about the maximum value which will be achieved for C2. So we see that as n tends to infinity, the maximum value which can be achieved, because there is a minus symbol here, so the maximum value will be 1 by 2. 1 by 2 minus 2 by n. So the maximum value of C2 as n tends to infinity can be half. So this is half. If we have to solve C1, then this is like a omega notation solving, and we have to find out the minimum value for C1. So we see that minimum value for C1 can be achieved when the value of n is 5. You can do it for the values of n less than 5. You will be finding that the minimum value is achieved when the n is 5. That is, when n is greater than equals to 5, then the minimum value, the value of 1 by 2 minus 2 by n keeps on decreasing. And so the value is achieved at n equals to 5. The point, the first instance where it is achieved. So if we solve like this, if we replace n by 5, we get C1 equals to 1 by 10. Now we have to replace C1 by 1 by 10, n value by n0 and C2 by half. If we solve this inequality, we will be finding n0 is greater than equals to 5. So if you have to solve the theta notations, then you can first use the concept of big zero to find out the value of C2. C2 will always be the maximum value, and C1, if we have to solve the C1 value, we can use the concept of omega, and C1 will always be the minimum value. Now, in the next slide, I have given some kind of problem statements. So you can go through this problem, you can go through the example problems, and you can try to solve these problems. And in case of any problem, as I told, you can come back. At the last, let us see what is the comparison of complexities. As I told, BIGO is the most popular one because it is the upper bound. It can also be called like it is used for representing the worst case. So what in case of the worst input sequence, what is going to be the complexity? And upper bound means, as I told, in case of linear search, so upper bound means if the elements, if this is the so if my elements are something like this, then if x is equals to 10, this is the base case. That is, base case means whatever will be the time taken for finding x equals to 0, it cannot go beyond that. So this can be represented by the omega notation. And if x is equals to 90 or 120, which is not there in the list, then that can be termed as the worst case, and that can be represented by big O, because big O gives us the upper bound. Because your complexity cannot go beyond this situation. This is the ultimate situation. So this can be termed as the worst case, and then this you can represent it by omega, because lower bound, because your complexity cannot go below this. It is a minimum time will be taken for doing this. So this is the lower bound. And this can be solved using the big O, because it is the upper bound, because your complexity cannot go beyond. So this can be termed as a upper bound, because your complexity cannot go beyond above this. So this is the maximum value. So this is the lower bound, or the minimum value, minimum time taken, or the minimum time required to solve this problem. And this is the upper bound, because this is the maximum time taken to solve this problem. So we can use this asymptotic notations for representing these two cases. Now, if we look at this diagram or this graph, you see the minimum is the log n. Next comes n. Next comes n log n. Next is n to the power c, that is n is variable but c is constant. Then c is constant, n is variable, and then at the maximum is n factorial. We can name each of these things. So this is linear, this is logarithmic, this is logarithmic. This time, this is known as linear. So order of n is linear. This is known as linear logarithmic. This is known as polynomial. Polynomial. And this is known as exponential time. So this is logarithmic time, this is linear time, this is linear logarithmic time, this is polynomial, this is exponential, and this is factorial. So factorial takes a maximum amount of time. And how can you distinguish between polynomial and exponential? In case of polynomial, this is going to be variable. So in polynomial, in case of polynomial, base is variable, but power is constant. While in case of exponential, base is constant, but power is variable. For example, we can talk of it like 2 to the power n. So this is exponential, and polynomial is n square, n cube, and dot. So I hope this video lecture is helpful to you, and you can go through the slides. In the next class, in the next lecture, we are going to start with the basic data structures, the linear data structure, which is known as array. Thank you very much.